Well, hello everyone, and welcome to today's Robotics Engineering Week session. I'm glad you could join us. My name is Dan Kerr. I'm the VP of the Robotics and Intelligent Systems Group here at WTWH Media. So today on the docket, we have motion control for healthcare robotics applications. Now, this is a very important subject, and I can tell you why. I mean, healthcare robotics shares many areas of technical commonality with electrically powered medical devices, as well as the common goal of improving patient care. A key difference, however, is that for all robotic systems, motion and movement in the physical world is expected and required. For robots, motion and motion control is presumed and it's definitional. As such, motion control technologies and techniques are central considerations for any robotics engineering initiative. Now, motion control for healthcare applications often have very, very different and very, very stringent functional requirements compared to other types of robotic systems in areas such as safety and reliability, tolerances, cleanability, and on and on and on. So the issues are real and need to be addressed. Good thing we have a great speaker today to cover some of these things, and I'll be introducing him in a couple of minutes, but first we have a couple of housekeeping items that we need to go through. So right off before we start, after this webinar ends, it will be available as a download on roboweeks.com. If you want to watch it again or share it with your colleagues, you just use the same login that you use to access this webinar on right now. You also have a couple of other boxes on your screen. There's a Q&A box and a resources box. The slides are available for viewing in the resources box. And then you can, during the, after the event, you can have time for question and answers if we have time. And you can type up questions and put them in the Q&A box that we can submit to the speaker. If we don't get to all your questions, the speaker can follow up through email. It's also it's important to note that you can move these windows around and they can be resized. So it's pretty nice interface for all this. Now, On24 is a web-based webinar platform, and it performs off your own user's internet and computer system. So if you're having difficulties, 90% of the time or even more than that, you can get them resolved by just simply refreshing your browser. You won't lose everything. It'll just pop back up again. And that usually solves all problems. But if you're still having difficulties, you can click on the Help widget. A couple of other announcements. There's the other offerings from WTWH Media's Robotics Group. As you can see, we have the top line there is kind of our print and online media, social media newsletters. So we have Robotics Business Review. It really focuses on the business of the robotics business, a lot of opinion and deep analysis and research covering all members of the robotics and artificial intelligence value chain. The flagship publication for the group is the Robot Report, both printed versions and online versions. It's really the best single source for breaking news and product information analysis and so on and so forth. We have printed supplements, there's downloaded reports. Go there every day. It's updated all the time. We also published a mobile robot guide. It's really the world's leading educational resource for autonomous mobile robots, AMRs, and their technologies and applications and suppliers. And then collaborative robotics trends, which focus on breaking news and information for users of collaborative robotics systems, as well as providers of those particular systems. We also have, of course, in 2022, we brought back our physical in-person events. Beginning in May of this year, we had the Robotics Summit event, which is for designers and developers of commercial class robotic systems, and it's an engineering event. And that is running again in May of 2023. It's also co-located with the Healthcare Robotics Engineering Forum, which, just as its name implies, is another engineering event. This one's focused on the engineering of commercial class healthcare robotic systems, however those defined, exoskeletons to interventional systems, and on and on and on. That is co-located. One ticket gets you into both events. We also have the Robo Business Conference and Exposition. We just finished it up in October out in Silicon Valley at the Santa Clara Convention Center. We'll be bringing that back in 2023 as well at the Santa Clara Convention Center, running in the fall of 2023. That will be co-located with the Field Robotics Engineering Forum, which focuses on the development of those systems that run in outdoor unstructured environments. So a lot of places for information and news, as well as meeting with your robotics peers as well. It's important to note that we also have available on demand the other sessions that we're running during Robotics Week this week. So you can see running from intelligent sensings for object recognition all the way down to today's sessions, which will be available on demand at roboweeks.com. So feel free, if you missed something there, you can always go to the sessions. We played them. They replay excellently. The notes are all there. The downloads, the resources are all there for you. I also like to thank our sponsors, our silver sponsor, Performance Motion Devices. They provide high-performance motion systems to OEMs. So they have a lot of advanced solutions for advanced robotics and automation, state-of-the-art torque control and positioning ICs for brushless DC brush stepper motors. They target multiple sectors: medical device, material handling, robotics, test and instrumentation, industrial automation, just on and on and on. They're also tied in with a number of healthcare robotic systems already: Intuitive Surgical, Da Vinci Surgical System, Zeus Surgical robotic system. Other silver sponsor is Electrocraft. It's a global supplier of application engineered fractional horsepower motor and motion solutions. They offer a wide range of technologies for OEMs, so AC, PMDC, BLDC, and stepper motors, gear reduction solutions, linear and rotary actuators, drive electronics, on and on. Like Performance Motion Devices, they have things that you can buy off the shelf. There's custom solutions you can also create. Our bronze sponsors today are Mouser Electronics, and then certainly Argo Robotics, which is a provider of sensing solutions. So great to thank our sponsors as well. And then finally, we have our speaker today. We have Prabh Gowrisankaran. He's the VP of Engineering and Strategy at Performance Motion Devices. You've seen him speak before, extremely knowledgeable about this particular topic. And we're very glad that we have him with us today to cover motion control for healthcare robotics applications. And with that, I'd like to hang over the presentation over to Prabh. Take it away.
Thanks, Dan. Thanks for the intro. This is a little bit longer. Typically, we've had multiple panelists, and so each person talks for 5 to 10 minutes. But this one's a little bit longer with 30 to 40 minutes, so I'll try to keep it light and not get boring. So just a quick background on Performance Motion Devices. So we've been around since '92. So as the slide shows, we control over 6.5 million motors. So we do a whole range of products all the way. You'll see it in the presentation. We do motion control boards and digital drives through amplifiers to ICs. So it all depends on the volume that your design requires. And we've been used by thousands of OEMs. We have, obviously, since we do a ton of medical, 50% of our revenue is medical, we have the ISO 13485 certification in addition to the ISO 9001. So what I thought we'll do for this session is just keep it more engineering focused. I stepped back and said, okay, what are the typical problems medical robotics applications are trying to solve? So the key for them, obviously with FDA and all the regulations, it has to be super reliable and it has to be efficient. So I looked at a few considerations that are there. So we looked at, this is applicable across medical to packaging to mobile robotics, but some of the keys are the weight. Make sure it's a small footprint and ease of use, because there's some that are battery operated and some that are used in surgical robotic settings. Power is always a key, where it has to be able to, one, for the heat generated, but also just in terms of the consumption. If you have to run it on a battery or you have to run it off some power source that's portable, and power becomes a key factor too. And heat being the last one, where you want the whole application to run cooler. It's cooler to the touch for the surgeon, for the operator, and obviously adds into the reliability of the machine. So one unique thing we've seen more and more people starting to use is these closed loop stepper applications. Just to highlight, obviously we do a whole broad range of applications across motor types. Just to highlight one use case where we've seen people go to this closed loop stepper to try and lower the noise and heat produced. And they get the higher position accuracy with putting an encoder on a stepper motor. And as the chart shows in the right, it lets the motor operate in its sweet spot, so you have low noise and less heat produced. So this is just a quick overview of things that I thought would be important for medical robotics applications. So what PMD kind of provides is we are basically a motion control partner. So typically, if you look in medical lab automation, medical device, medical robotics, their focus is on the science or the biology of it, to either detecting cells, detecting cancerous tissues, or whatever the end medical use case is. For them, motion is almost, they want to just buy it and able to use it. So they look for a trusted partner. So we tend to work really closely with a lot of these OEMs. We actually sit down with them, kind of walk through the block diagram with them, and kind of look through what algorithms they need for motion control. Obviously, we do all the advanced motion control algorithms like S-curve, FOC, current control, as the third bubble shows. And we become like a trusted partner. And you will see further down in the presentation, they start off with a board that they can prototype with, prove the concept, make sure it works. And as the volumes go up, then they can design their own boards with our drives or ICs. So we tend to help them throughout the process. We provide a lot of design material. We do design reviews with them. And our claim to fame is our C-Motion, which is a C-based SDK that's provided to all our customers. So that way, once they implement one project, they can easily migrate that to other products. So we have a few medical companies that have developed their own single-axis motion card that they tend to use across machines. And along with that, they're able to take the C code that they've written and put it over to other applications. So it kind of gives them like a basic building block that they can build on, and then can easily, quickly go on to building other machines. So for this particular presentation, it's a little bit longer presentation. So I said, okay, let's take a look at what is a typical robotic motion design challenge. Some of the things that stood out to me, before this, I was actually in a robotic 3D printing startup. I ran a robotic 3D printing startup. And this Cartesian versus non-Cartesian motion management was a big deal. Because for 3D printing, we used to slice the layers, and then trying to translate them into a non-Cartesian space was a lot of math. And it was a tough problem to solve. So that was the first design challenge that I thought of. The second one is this dynamic load management, where you have an end effector and you have variable load. How do you manage and get to precise motion control in those situations? That's the second topic we'd look at. The third one is one that I alluded to before, where it was like a build versus buy kind of decision. Okay, when do you build your own card, whereas buying something off the shelf that's much easier, that's already fully integrated? So we'll walk through some of the parameters for a build versus buy. And then we'll end it with a few other design challenges. And I always like to look at application examples. What does a typical card look like? How do they implement it? So with that, we'll dive into the first motion design challenge. This is the non-Cartesian motion management, where obviously you have the path planning and then inverse kinematics that come into play. So just giving a quick background, right? Cartesian motion is like a gantry, which is a clean XY motion. So you have, if you think of an XY table, if you look at a lot of lab automation, there's pipettes there that you move in X and Y and Z to pick up a sample, and you drop it off somewhere for testing. So it's a very typical XYZ kind of motion. That's what Cartesian motion is. And as you see, if you add the Z-axis, it becomes a gantry. Otherwise, you have an XY table. Whereas the non-Cartesian motion is a little bit more involved. It's a typical robot that you can think of. If you look up a bigger KUKA, ABB, one of the Orphanic 6-axis robots or 4-axis robots, it's almost like it's a robotic arm, right? And you have, if you think of it, there's 4 axes of motion in a scalar robot. So you have, as you can see in the chart in the right, there's a lot of math equations to figure out the X and Y positions. So you have the shoulder and the elbow has rotary motion that you calculate through sine cosine algorithms to get to actual XY points in a Cartesian plane. And so in a scare arm, it operates in a Cartesian workspace. It operates in an XY workspace, but the axes are all controlling angles and they have non-Cartesian elements to them. So typically what you would find is there's a whole bunch of inverse kinematics math that has to be done somewhere, right? In a scare arm, it's either done by the host, and then they send specific motion commands to each of these axes, or it could be done in the controller, but then you need more compute in the motion controller. So we will take a look at a few ways we've seen and helped some of our customers solve this non-Cartesian and inverse kinematics issues. The other problem we see is when you have an arm and a shoulder, is you have the linkages result in like complex profiles. Because of the non-Cartesian motion, there's mechanical linkages. The motors rotate faster at some points and slower at other points. And so to traverse a straight line path is actually pretty complex. You have a lot of math involved to kind of compute these X, Ys and get to a nice, clean, smooth motion. So if you look at a profile for motion, it's actually more complex. It's neither, like our chips support a standard S-curve or trapezoidal profile, but these are neither S-curve or trapezoidal. They are like a little bit more complex than a traditional profile. So you have to continuously tailor your commanded position to kind of get to that straight line motion. So as the chart on the right shows, you can see the shoulder velocity to go from XY one location to the other. You can see the chart of what the shoulder and elbow velocity look like. They are nonlinear, and they're taking into effect the effects of the linkages and the mechanical variations in there. So obviously the solutions we've seen, right? If you take a traditional scare arm, you could do all this inverse kinematics math in your host and try to send specific motion commands to each of these axes. So you could potentially do all this math in software. Obviously, the math this is just a snapshot. There's actually a detailed white paper we have that talks about how to solve this. But the problem is, on an off-the-shelf motion controller, it's hard to have all this computed for every point-to-point move. So that's a big challenge in an off-the-shelf motion controller. So the other approach people have taken is a segmented profile approach. Like they take a path and segment it into really small chunks of motion. And so you break them into pieces and then you try to fit them into a standard profile, like a trapezoid, to create a complex shape. And as you can see, the main downside is there's a lot of supervisory software requirement, right? You have to know when you've completed one segment and when you're supposed to move to the next segment. And it's not as smooth as a true inverse kinematics motion. So you could do this with breakpoints. So we have had some customers do this where if the path is not as critical as they're moving, but more the endpoint is critical, they've broken them into segmented profiles and programmed them into a motion controller to get this motion done. What we've suggested, what we have in our motion controller is this translation lookup tables. So as the animation shows on the right, you could create a table for every XY. So that it basically works as like a lookup table where it makes an inverse kinematic engine. So for a scare arm, you could convert XY commands to phi and theta commands for your elbow and shoulder. And you can make a two-dimensional translation table. And the table can have a specific amount of points, and then you do the lookup to do this inverse kinematics. So this is one approach that we've seen. We've helped customers through customization on our ICs to add these lookup tables to do the inverse kinematics without having to do the math. So they would compute these translations ahead of time, and they would populate it in the off-the-shelf motion controller, and then you can execute non-Cartesian motion that way. So that was just a very quick overview of the inverse kinematics problem that you have in a traditional robot. The second problem that we typically see is dynamic load management, where for whatever there's either you have intelligent feed-forward requirements or compliance compensation. We've seen cases where the mechanical construction, it's nonlinear, but if you want smooth motion, you want to be able to offset some of the nonlinearity with compensation tables. And we've seen cases where they cannot put an encoder right at the motor. It's through a camming or a gear at a farther end. There's a linear or an optical encoder somewhere. So there's translation differences in terms of end position. And we've seen people put compensation tables to solve that. So we've helped customers through trying to define the system level problem. Where is the motor? Where is the encoder? And what does your load look like? So like this one talks about this dynamic load management. Even though you tune your PID loops for your motor and your motion, it's hard to track the desired profile at the load because there's a lag, there's an acceleration phase, there's a little bit of overshoot, and then there's a deceleration phase. So that's what these charts kind of show on the right. And then you also have, like I talked about, these compliant linkages affect position accuracy because you're commanding position at a motor and then it goes through a camming or there's some sort of mechanical chain or something before it hits the load. What you really care about is the precise motion of the load. And so there's some translation that has to happen to compensate for this nonlinearity. So this mapping the relationship of torque to deflection, which we can add compensation tables to our position and PID loops to get you to smooth motion across these use cases. So typically what we've done is there's a ton of what we do is they characterize the mechanical, the mechatronics and the mechanical construction, and then we add feed-forward terms. So this example, it actually has a torque to deflection table. There's a feed-forward term that's added to your profile generator. So you basically introduce it by adding it to the PID loop, and then that accounts for it takes the difference and accounts for a nice, clean, smooth motion. So this is one common technique that's used. We could apply these compensation tables at different points in the position loop, depending on your mechanical system and your construction. So this is a very popular use case. We've also seen use cases where they're trying to design like a micrometer or a nanometer precision machine, but they don't want to use an absolute encoder because those are expensive. So they tend to use cheaper encoders, but try to compensate for the inaccuracies of the encoder. So if they can characterize it in the bench, they can put a cheaper encoder, make the machine cost cheaper, and add these compensation tables to account for the differences to get to the precision that you need in the motion. So there's some techniques that you could do in the controller to offset and make the machine design costs cheaper. So that was just the first two. So we looked at the inverse kinematics problem. We did the translation lookup table to kind of solve that problem. And then you had the compliance and the linkage issues. You were able to compensate it with adding feed-forward compensation tables in the controller. A pretty typical question we get is this build versus buy. And we added this thing called blend, where do you build your own card and your own controller and motion control versus buying it off the shelf versus having a hybrid approach. So to look at this, we said, okay, let's take a design example. Let's take a 3-axis motion controller, right? So we went through an effort. There's actually a very detailed white paper on our website that you can download where we went through the idea of designing a 3-axis motion controller. One was buying the card outright with everything. The other was designing your own card. Another was a blend where you use an intelligent drive and then the card design itself becomes minimal. So this is a very common request that we get. And the other thing we tend to see is people start with buying the card and then transition as volumes go up to building their own. So this kind of, I'm trying to highlight the progression of a design. So the common theme that comes in is when they look at build versus buy, they have to look at, do you want a centralized control or a distributed kind of control? So if you take a robotic arm, you could put a controller right at each axis and just have power and communications, either CAN or Ethernet, go from axis to axis. The other approach you see, like the ABBs and the KUKAs of the world, is they have a huge central controller, and that computes everything and just is sending PBT commands to each axis. So those are two kind of approaches that are there for control, and that kind of determines your build versus buy decision too, right? If you have distributed control, you probably can go with the blend approach. If it's centralized, you have both options. You can do a build versus buy of a card. So this is just to highlight the few different approaches to building your machine. So if you look at the example case we talked about, we said, okay, let's take a 3-axis PCB, right? It's trying to do 2 BLDC axes and 1 step motor axis. And you obviously have a bunch of digital I/O, you have e-stop and brake and stuff, and you have a system host interface. So this is a typical example control card that you have for lab automation or medical applications. And so we just said, okay, what would it take for us to build it, right? So we tried to highlight all the project development steps, right? You'd have to pick out your connectors, the wiring, you have to buy or build your own, design your motor amplifier, you have to pick your IC or design your own FPGA or DSP base, then do the schematic and the layout. And then on top of that, you have to write software, right, to do, and you have to implement all the FOC and current control stuff in your own design. And then you have to write application software on top. So this is what it takes to design a motion control project. So we then looked at trying to, if you had to build it, say you built your own card, you could buy a motion IC, like our 58113 IC has all the FOC and current control and all the control algorithms built in. And you could plop that down and then get an amplifier that it mates with, and the two together can control an axis. And so this is all, the build decision comes down to, okay, do we have design expertise in-house? Do I have analog design capability? So you had to kind of go through the capabilities that you have in-house and what the design looks like. So if you look at the build option, so where you are basically doing all of it, right? You're picking the connectors, you're designing your own amplifier, either building or buying your own IC, and doing all of it. We said, okay, what's the design effort? This table on the right kind of gives you an estimate. It's like roughly 34 to 60 man-months to do the design. And we tried to break it down into what the costs are in terms of man-months to design and what additional expenses are as part of the design. So this is the build option where you're doing everything on your own. In the buy option, where on as the graphic shows, it's a card we sell. It's a 4-axis machine controller card. It's a Prodigy card that has 4-axis our Magellan chipset and 4 amplifiers. So in this case, there's no hardware development per se, right? You're mainly working on application software and the motion control parameters and tuning of your motors. And in the cost here is the 10 to 16 man-months in terms of your design effort and in the software side, and there's no additional expense on your side for the design. And it's getting more and more, the blend option is getting more popular, where people still want the capability to customize their card because they want to have their own connectors for connecting to their encoders and motors. But so the card itself becomes a much simpler design. It's like a 4-layer card. You plug this intelligent drive in. This has all the controls. It has a host processor, and you're just doing a simple passive card with the right set of connectors for all the things you have. So you have the power, you have host communication connection, you have motor connection and encoder connections, and any other sensors that you have. So that's all the card is in terms of, it's just the passive connectors you want. But this gets them a level of customization that they look for. And they can plug these 1 per axis. So this blends itself to a distributed control approach, but you can also do it for a centralized approach. So this is in between in terms of the number of man-months required and the associated expense. So so if you look at this is what that card would look like. If you look at the intelligent drive, a blend card, it has 3 of these drives, it has some bulk capacitance, and it has the connectors that you want. For your host connection, this kind of shows what the block diagram looks like. And each of these drives do a kilowatt of power and control. So this is a simple hardware design. The software is distributed, and then so this gets you to the market quicker, with still keeping the customization that you need. So this is just a quick summary. Obviously, what we've seen typically people do is a lot of startups, healthcare, medical robotics guys would start off with the buy. They would buy a Prodigy controller card and get to prototyping quickly so they can do a proof of concept, write their software, and then in parallel, either do a blend with our intelligent drives or do a build, full-blown build with an ICs and their own amplifier design. And typically what that decision point comes down to is the final volume. If the volume is 1,000 pieces or less of your machine, then the blend works. And if it's really high volume, then a build option works. So we've seen customers kind of start in the middle with the buy for prototyping and then transition to either build or the blend. So there's a white paper in our website that kind of walks through this in detail. So it's a common, even we go through this for some of our designs, whether we want to build everything from scratch or do you want to buy from some of the providers. So this is just to give you a high level view of a build versus buy versus blend kind of decision for motion control. So with that, we covered the first 3 points in our agenda. So I'll move on to a few other design challenges. So one of the bigger design challenges, the first one we talked about was size, where everything is getting miniaturized. So this is just giving you an anecdotal comparison, right? This is the drive that we had 10 years back. It's 4 times the size with 500 watts of power. Whereas the newer drive, which is the intelligent drive, which is solderable, is a kilowatt of power. And all this is achievable because you have the electronics, the controls from all the iPhones and smartphones have improved capabilities in all the chips. So we are able to shrink the overall footprint. And obviously we packed the amplifier in this. So this is a fully has everything, has the motion control, has a host processor, and the amplifier that you need to control a motor. So there's a lot of man-months that have gone into making the amplifier as small as we can. And obviously heat's a concern, so we had packaged it so that it's in such a way that you could run up to 20 amps of current with no issues in this drive. So this, just to highlight, this is the newest product that PMD offers, which goes into the blend approach, which is an intelligent N series drive. So it's a 3-card stack. It has digital connector pins and then the power connections, and it can go up to a kilowatt, and it provides a whole host range of host interfaces from CAN to Ethernet to serial. And on the motor side, you could talk to brushless, brushed, or a stepper motor. So when you're designing a healthcare robotics use case where you have, most of them are brushless motors, but there's a handful of stepper motors, you can use the same drive and just in NVRAM set them to what motor type and intelligently configure each of these drives. So this is just a little bit deeper dive into what's internals of this drive. So it has a host processor where you can actually write C code and download it to the host on the drive. So what it allows you to do is the central controller can send really high-level commands, saying high-level motion of axes. You can download the feed-forward compensation tables for each axis specific to its own host controller. So it can do all the compensations local to the axes. It has our Magellan motion control IC in there, and then it has the power amplifier design. And what we're starting to see is more and more designs go to using more advanced encoders. So we see nanometer and micrometer stages, like microscope stages, use sine cosine for precision, so which is natively supported in this drive. And in Europe, BIS-C, which is a serial encoder, where you can daisy chain encoders, is pretty popular. So this supports BIS as an interface for an encoder out the box. The other common request we get for safety is having two separate power supplies. So there's an HV for high power for running the motors and the amplifier, and there's an HV aux for the digital side. So that way, if you have a safety event, we can shut off HV, and you can keep HV aux running for safety and reporting and collecting stats and predictive maintenance and stuff. So you have the capability. You can either run it all on one power voltage, one HV supply, or you can split it as HV and HV aux for safety purposes. So there's a lot that we packed into these N-series digital drives, and it lends itself to you can either do a centralized control or distributed control. And we also added this, you can have expansion networks where you could talk to the host on one, and then the first unit becomes the master. It looks like a multi-axis controller. And then we have an expansion network that you can plug in multiple of these N-series drives to control other axes. So as a host, you're just talking, looks like you're talking to a 4-axis machine, and it does the translation and controls the remote axes. So there's a lot of sophistication in this drive in terms of intelligent expansion network control. And obviously, in these use cases where they want a standalone kind of a battery operated use case in medical, so you could take one of these drives and put it in a handheld with a battery, and you can download all the code, the 4 controls, onto the drive itself. And so you don't need any other host interface, and that can do your pre-programmed controls. So this is we have a couple of customers that are looking into battery operated handheld kind of applications. With that, I'll try to kind of walk through. So this was the other one where we talked about the distributed control. So in this one, where you put the remote N-series drives on this expansion network, and you can actually send commands, more high-level commands to the remote axes, and you can initiate modes. So with that, we're getting close to the end of the presentation. So I usually like to look at a few application examples. What does a real implementation look like? So this was the one where we talked about the distributed control. So this is a robotic arm with either a collaborative robot or one of the medical surgical robots. So at each axis, you can see there's a image shown of the card, the size of the card. The N-series drive has all the intelligence in it. So all you have is connectors and some bulk capacitance outside, and you can put them right at the axes. And this kind of shows what is in the card. And the advantage of this is also for maintenance, you're able to replace just the drive and the motor and the controller on each axis independently. And when you swap them out, you can actually assign, it automatically detects a new one, and it assigns all the parameters to it, and it takes the identity of that axis controller. So this is a robotic arm, which is very common in the surgical robotic space. The other one that we see a lot of is any XYZ gantry kind of application in lab automation, liquid handling. And this is kind of showing the other approach where you have a centralized card where all the controls are in one card. So this shows the layout of the card. It has 3 drives. It's doing the XYZ control, and all the cabling is running through. And so each of the motors, the encoders are all wired back to the controller. And as you can see, it shows the scale of the actual controller design. It's pretty small compared to the overall gantry. And from a maintenance point of view, it's easy to replace the card. So these are two pretty common applications in the medical space. One's the surgical robotics space with the distributed control, and the other is the centralized control for lab automation. So with that, I just want to kind of summarize what we looked at. Obviously, there's a lot of other unique challenges that you have for every design. We tend to work with you to kind of look through the block diagram, identify the challenges. Obviously, we've worked with thousands of OEMs, so we know we've encountered these challenges before at some OEM or other, and we can become your motion control partner to kind of help solve your problem and figure out what encoders to use, what motors. If, for example, we cannot put an encoder in a motor, and if it's further away, what kind of compensation you need. So we looked at, quickly summarizing the presentation, we looked at the non-Cartesian and the inverse kinematics design challenge, and we suggested a translation lookup table approach to solve it. We looked at feed-forward techniques for intelligence, compliance management, and nonlinearity management. And then we, at the end, kind of looked at the latest product from PMD, which is a PCB mountable intelligent drive, which provides you user programmable code where you can program all these translation tables and store them and ship it as that. And we also introduced the idea of hierarchical architecture where you can have the remote axes on the expansion network. So with that, I would hand it back to Dan for Q&A.
Well, that was great, Prabh. I like that you finished up with some real-world examples. We do have a couple of questions that came across that I'd like to posit to you right now. The first one was regarding the design challenge, the build versus buy. What are the current trends in the U.S. and European marketplace with regard to buying, building, or the hybrid approach that you described?
Yeah, so what we've seen both in the US and Europe, they almost always start with the buy. So there's a time crunch to prototype because they have to do a proof of concept, even to their senior management, to show that the control architecture works. They start with that and then decide based on volumes. So they work with product management and kind of try to forecast. And if they know the volumes are more than 1,000, then they immediately start with the build option in parallel. But if they're not sure, or then they kind of stay with the buy and just wait it out and postpone the decision to build later. The nice part they have is the same software that they do on the bill, right? Like if they bought the card and they write all the C code, can be ported over to their own card. So 90% of their software design is done and they can port it out. But with this intelligent drives, we are seeing more and more of the blend because that gives them the benefit of both worlds, right? They typically want a plug and play card where they have the right connectors, all the motors plug in easily. They don't have to do adapter cables and stuff. So we're starting to see a trend towards the blend where they buy the intelligent drive, they do a passive card, and then so they can at least get the design going quicker. So that's what we're seeing more and more of now.
Okay, great. Can you comment on some of the benefits of a distributed versus centralized motor control in cobots and in robots?
Yeah, so typically if you take a look at the big guys, right, like ABB, FANUC, and KUKA, and those guys, it was all centralized control. And then they would have to do PVT, like the central controller would calculate the PVT terms for each axis, and then would have to stream it to each of the axes. So the speed at which they send is very critical, and the wiring. So they're sending more information from the central controller to each of the axes. So there's a lot more wiring. But a lot of the cobots and the smaller robots, like some of the newer designs, like surgical robots, are going to this distributed architecture where if you look at it, the motor and the controller are right there. So there's all the cables, the motor connections, the encoder are pretty short and they're local to the axes. And it gives them a lot more freedom of motion. The only thing they're sending is power and communication, like CAN or Ethernet from axis to axis. So it simplifies their machine design. Like if you look at the robot, they have to fit a lot more things in there. So having this distributed architecture really helps them. So I think newer designs are moving to distributed, but the traditional designs are all centralized.
Great. So, can you synchronize motion across multiple axes?
Yeah, so this, you can do them depending on the level of synchronization they need. So we offer, there's like actual separate signal that goes from axis to axis that would synchronize the clocks on each of these drives. So they are lockstep. There's also commands that you can send across to synchronize. So we have, it's very common request because if you look at some of the profiles, XYZ, especially in the non-Cartesian motion, there's a lot of interactivity between all axes. So they have to be synchronized. So we do that it's a typical requirement. It's very rarely do people, when they're designing a healthcare robot, not need synchronization. It's a very common request.
We have a question here asking, do you support path planning and other custom motion features?
Yeah, so we do path planning in what we do is we call it user-defined profile mode. So what it is say ahead of time, you know the paths, so you can load them in a table. So if you did this N-series drive, right, an intelligent drive, you can actually load all the points that you want to traverse, all the different paths into a table. So you can plan, we provide path planning capability, and you can load them into a table. So what happens is after this particular move is done, you move on to the next one in the table and so on and so forth. So without having any host intervention, you can execute a whole path on your own. And actually, there was one healthcare surgical robotics presentation that I was a part of, where one of the surgeons was saying what ends up happening is they would do a set of moves, right? So they're trying to do some sort of surgery, and at some point they reach a decision. They decide, okay, whether they want to do the next set of moves or should they be different. So you can do that level of intelligence where you can go down a set of moves and put a breakpoint saying, okay, go back to the host, and the host can tell you which can create a tree. You can either do this set of moves or the other ones. And so there's a lot of intelligence that you can add to which set of moves you want to do it, depending on decision points. Because it seems in surgery, it's pretty common. They would do a common set of moves, get to a point, and based on what they observe, decide to continue the surgery or retract back. So it changes in situ as they are doing the surgery.
Great. Let me ask a question. Then you might have touched on this at the end of your particular talk. When in the design process do companies make the build or buy decision?
Typically what we've seen is they tend, if it's a large OEM, right? Like let's say one of the big medical guys, and they're designing a brand new platform, and that's going to get used across, let's say, gene sequencing or genomics or whatever. Those cases, they tend to start with the build because they know it's a platform they're building, and they know they're going to sell 1,000 plus of those, and it's a building block for them. Then they prototype with our DKs, the cards we provide with ICs, and they start the build of the hardware in parallel. But most of the mobile robotics guys, what they end up doing is the blend where they put the drives. So they build a card with just the drives, and they can easily change that card. So they would start with a certain form factor in mind. So if you take one of the mobile robotics guys, they would have 2-axle control. So they would put 2 of these drives in a card. And it gives them the freedom. Later on, they can try out 4 individual wheel control. So they can do 2 different flavors without much complexity. And then they would decide, okay, which one to build as they move forward. So what we've typically seen is really large OEMs start with the build right away. The lower volume, unique use cases tend to stay on the buy side.
Got it. So, there's a follow-up question here. Is there a path to buy for low volume and later on move to build for higher volume?
Yes, a lot of people do that because if you look at the length of a project development, the software and the system design is the longest. So with the buy, they would buy the card, and they're able to do all their software development on it. So it has 4-axis control with amplifiers. They bought it off the shelf from PMD. They can write all their software for higher level access controls, compensation, and all that. And later on, when volumes go up, they could build their own card and port all this code over because it's the exact same the C motion library stays the same, and so they can run, and our ICs run the same, which is the big benefit that we see. So for a startup, they tend to start with a buy, right? It's so they don't have, it's not 2 years for you to have a final solution. You can have something in 6 months. You can do a proof of concept, show it to the VCs, and once you prove that there's a market for it, then they can start the build. And the nice part is being able to use all the software over into, and usually the system problems like the compensation tables, the linkage stuff, the inverse kinematics are bigger problems. So it's much better to buy and prototype and identify all the problems you have in your machine before the build decision, because they could change their mind from a centralized to distributed, right? So when they build their own, they could switch it to a distributed architecture depending on the machine design. It's very interesting. Sometimes the mechanical design guys have a bigger input into the architecture because of the cabling and the structure of the motor and all that stuff and the cooling. So the distributed or centralized, sometimes they do it a little bit later in the design phase.
So for PMD, will you help customize your solutions if a customer comes to you and decides to go the buy route? Is there customization available?
Yeah, so we do a ton of firmware customization. So we obviously, all these compensation tables and stuff, we have a library of them, but based on the end user use case, right? Once they build a machine, they want unique compensations done, we do that. We work with them, we make custom firmware, and they can buy that particular version of the chip. And we've also worked with customers on customizing the hardware. So if you take like our 4-axis control card and they want to kind of design their own, we have third-party design houses that would actually take that design and make it the end OEM's design. So we work both ways. So there's a lot of customization that happens in terms of the firmware features, or they want unique I/O, because there's only X amount of, there's 8 digital I/O and analog I/O in the drive. They want to do unique things like brake for safety, the brake ties in with other functions. So there's a lot of unique capability that they want. If they don't have their own host, we can do all that customization in our drive.
Excellent. Oh, cool. So maybe you could just briefly describe the process. So if a company comes to you with an idea for a medical device or a robotics device, how does that work? Can you describe it based in large chunks, basically the product? Like how soon should they come to you? How do you engage with them?
Yeah, typically we actually, once they have a concept in mind of what it is, we like to engage earlier because we could help them pick the motors, the encoder, right, and the mechanical design. So we tend to work with them, like even a block diagram level. It says, oh, there's 4 motors we're going to control. They're going to do these things, right? They haven't picked the motor. They haven't picked the encoder. They haven't picked what controls are required. We typically start at that level. So we are kind of sitting with them and looking at the block diagram and saying, okay, based on our experience, these are the motors you should use. This is what the design would look like, and provide them feedback. And then as they progress through, we help them with the schematic reviews and layout if they're going to build their own, or we kind of show them which products they could use. And we also help them kind of prototype on the bench, right? With all these drives have DK, like individual cards, they can just connect them on the bench and prove out, which we recommend a lot to these customers, where we kind of help them prototype something on a bench. So we work really closely with them in kind of walking through. So the earlier on, it's better because once the mechanical design is set, then they're struggling to fit their cards and electrical design into that machine design. Then it's very hard for them to kind of retrofit it in. So it's a lot easier when they're in the concept phase early on.
Okay. Well, that's about it for the questions. So I would like to, thank today's speaker, Prabh Gowrisankaran, VP of Engineering and Strategy at Performance Motion Devices. I'd also like to thank our sponsors, Performance Motion Devices and Electrocraft and Mauser Electronics and Argo Robotics for all of this. And also thank all of you who attended today's webinar. And then as you can see from the slide here, that all of these presentations from this week's Robotics Engineering Week sessions are available for on demand at roboweeks.com. So if you're interested in attending them, just sign up and log back in. And with that, I'd like to thank again our producer, Matt Boblet. He's been excellent over the whole week for doing this. And for myself, thank you very much for attending, and I hope to see you soon in a future Robotics Engineering Week session. Thank you.
Thanks a lot, Ted.